My name is John Ackerman. I'm a sophomore at the University of Connecticut, and I'm double majoring in mathematics and statistical data science. And I'm going to be presenting on the data cleaning of the data. So I wanted to start by just giving an overview of why data cleaning matters in the first place. And I have an analogy over here to the left with these images. So imagine that you're trying to bake a cake. No matter how good your recipe is, and no matter how good you follow it, if you're working with faulty ingredients, then you're not going to end up with a good product. And it's the same thing with data. So if we have data with redundancy or missing values or other sorts of inaccuracies, then no matter how good our analysis is, uh, you can never fully trust the results that you're getting out of your data. All right, so the raw data set that we're working with is the NYC open data of 311 service requests from 2010 to the present, except we're just going to be focusing on the sewer-related complaints in 2024. There are two types of complaints: the street flooding complaints, or SF, or catch basin complaints, CB. Some key data fields are the complaint type, which is SF or CB, when the complaint was reported and when it was resolved, where the issue occurred, and there are three different location type variables we're going to be using: coordinates, zip code, and borough. And for the analysis, we're going to be using Python, and there will be a link to the code at the end. All right, so there are five types of data cleaning I'm going to be going over. The first being data consistency and naming conventions, then summarizing the missing information, looking at redundant information, looking at missing or invalid NYC zip code or borough values, and finally, errors with the dates. Okay, so data consistency and naming conventions. It's important that we have some kind of consistency in the way that we're naming things. And for that reason, I've taken the NYC data and I've changed it so that we no longer have capital letters, and we also change these spaces to underscores. And this is helpful because it keeps things very consistent, it's easy to read, and it works across all programming languages, since sometimes having spaces in your variable names causes issues if you're trying to automate something. And these changes may seem minor, but they reduce mental effort and they can help with teamwork and collaboration. And then also, when your data set gets very large, it's important that you have a nice, clean foundation to build off of. All right, so now we're going to be looking at some missing information in the data. What I found is that a lot of the variables are either mostly full or almost entirely empty. And we can look at what are the most empty variables, and it turns out there are actually 11 variables of the 41 original variables that are just completely empty, which means that we can just remove them from our data set at no cost whatsoever. There are also some variables that, like intersection street 1, that are only 76% empty. And while there's a lot of things missing, I don't think it's necessarily a good idea to remove them entirely, because we could transform these variables maybe to like a binary variable, and maybe that would come in handy during our analysis. All right, so now we're going to be looking at the redundant information in the data. And this matters because if values are overrepresented, it can introduce some kind of bias to our data. And also, this extra unnecessary data increases our memory usage, and it's going to make it harder or longer to run functions and such. So it's just a good idea to clean things up. All right, so these are all different types of redundancy that I checked using Python code. So the first being, I looked for duplicate rows, just rows that for whatever reason are same in every variable, and there are actually none of those. I found that there were two pairs of columns that were highly correlated, that being the x coordinate state plane and the longitude, and then the y coordinate state plane and the latitude. And this makes sense because those are just two location coordinate systems. So it makes sense that there's going to be almost a perfect correlation between those two ways of location. And then finally, we looked for columns with exactly one unique value, and those ended up being agency name, complaint type, and park facility name. And not all of these are necessarily an issue with the data, because obviously we're taking a subset. So we're always going to have the complaint type be sewer, for example, because we're only looking at the SF and the CB data. Forget, I was gonna click. Okay. All right, so there are some other redundant columns that aren't necessarily numeric. So they didn't show up when we were looking for correlation, but those are, for example, latitude and longitude and location. So you can see that latitude and longitude are just values, and then location is this like pair of values, right? But it doesn't necessarily, we don't necessarily need both latitude and longitude and location in our data. And then park and park borough, those always just ended up being the same borough. Agency and agency name, obviously one is an acronym and the other is the full thing, but once again, they encode the same information. And then finally, we found that cross street 1 and 2 and intersection street 1 and 2, while they weren't always the same, there was a very, very high correlation between the pairs of variables there. All right, so then missing and invalid zip code or borough data. So the data contained 3 types of location variables, as I said, and we'd like to make sure that all the complaints are within New York City, and then fill in any missing data, if possible, using other location data. So first, we're going to try to see if all the complaints are within New York City. So what I did was I took a list that I found on the New York City Department of Health's UHF codes, and then I looked in the data to figure out which of the zip codes didn't fall within that list of proper zip codes that I had accumulated. And I ended up getting this list here, and you can see that some of them appear quite often. So then I cross-referenced that with a couple of other sources and ended up finding that there were actually 2 zip codes, those being 11,001 and 11,040, which are both located in Nassau County, which is outside of New York. So I believe that those should be taken out of the New York City data set. And then for borough, you can see here that there were 2 cases that had two complaints that had borough unspecified, which doesn't give us any information about what the true borough is. So we're going to have to rely on a different method for finding that borough, which is maybe we can infer the location using some other data, right? So if we don't know what borough is, but there are more specific types of location like coordinates or zip code that we could then use to figure out borough. But unfortunately, you can see here that there were 5 cases that I've come up with, and all of the complaints either had all of the information or they were only missing the borough and those remaining they only had borough in the remaining 4 cases, which means that we can't do anything to save those complaints. Then date errors. So there were 2 date time variables, which was the created date and the closed date. In my analysis, I searched for 3 types of date errors, which was, which is whether when the closed date is earlier than the created date, which is obviously a big problem. That happened once. Then if the created date and the closed date match to the exact second, and that happened 160 times, then the final is if created date or closed date were exactly at midnight or noon to the second, which because we're looking at, we're eventually going to be looking at the difference between those 2 values. If we get the sense that people are approximating it, then we can't trust that data as much. And hopefully there will be some sort of overlap between these 3 violations, but it turns out that there actually was none, and there are a total of 363 rows that had at least one of these date errors. So given the importance of the date variable in our analysis, which you'll see later, I recommend that these rows be removed. All right, so finally, my overall suggestions to the data creator, I have a few. The first would be to consider moving empty columns to agency-specific tables. So something like there was a variable on taxi, and that doesn't necessarily belong in the sewer complaints. Another suggestion would be to create a software to auto-populate the created date or closed date columns. So you remember that there were issues, it seemed like, with the way that these were being encoded. So it might be possible to design something that could automatically input these values into data, and then hopefully that could just stop these issues at the source. Second to last is to remove the redundant columns. So my suggestion would be to take out agency name, park borough, location, and intersection street 1 and 2. And then finally, to investigate why and how these issues happen to begin with to hopefully stop them from happening in the first place.
So I covered part 2 of the project. I'm going to be taking you all through an exploratory analysis of the service request flood data that John just cleaned for us. All right. First, I'll introduce myself. My name is Tom Scatina. I'm a senior at UConn, set to graduate this May with a degree in statistics and a minor in mathematics. Hopefully, I'm planning to return to school for a master's in statistics within a couple of years. Much of my coursework up to this point has been rooted in classical statistics, a lot of the mathematical foundation. So this is actually one of my first fully fledged data science projects, and I hope you all enjoy it. I'll give you all a quick outline of what I'm going to be talking about today. We're going to start with visualizations, mostly, of the complaints, where they were located in New York City, as well as we're going to look at some histograms to see different frequencies and such. We're going to be working with 2 new variables that we're going to construct from the existing data, response time, and then this one at the bottom here, over 3D, which you'll see later is just shorthand for over 3 days. And then the second half, we're going to focus on some hypothesis testing to get an idea of the relationships between our target variables and the predictor variables. Okay. So first, once this loads in, this is a Google map of New York City with all the different incidents plotted onto it. So the red points are the street floods and the blue are the clogged basins. And we can see a couple things from this visual. First of all, just the relative frequency of clogged basins compared to street floods. They're clearly much more frequent. And we can also identify some hotspots, such as on the Rockaways down here. And it is an interactive map, so we can zoom in, hopefully, and we can see that, not surprisingly, there is very dense, high density of these incidents along Bell Harbor and the Rockaways, which makes sense because that is right along the ocean. Next, we're going to construct a new variable, response time, and visualize that. So this variable is going to be constructed from the 2 columns that John mentioned earlier, the closed day and created date. We're simply going to subtract those 2 to get the response time. And down here is just a snapshot of the data table. So you can see we've added that new variable, response time. And currently it's in a days, hours, minutes, seconds format. For the sake of visualization, we are going to convert that. We're converting it to hours, which is just going to be a little bit easier to graph. But you can see clearly there's a problem with just trying to graph the raw data as it is, because we have some very large outliers. We have cases where the response time is 6,000 hours, which messes with the scale of our histograms. And it kind of truncates or shrinks all of the data into the bottom left of our histogram, which isn't very interpretable, and there's not much conclusions we can draw from that. So the quickest way to deal with this issue is just a transformation of the data. Instead of using the raw data, we can take the square root of the response times, and we can also drop the 3 largest outliers, and we get a much cleaner picture of the data. So here we have the response times in hours, the square root of that, and then we have it for both street floods and clogged basins being on the left, street floods being on the right. And we can see that there is a exponential or gamma type distribution. You see it rises quickly and then drops more gradually as response time increases. And those 2 histograms were separated based on the type of complaint, whether it was a street flood or a clogged basin. But we can do the same thing for the different boroughs. So we have 5 histograms here, 1 for each borough. And we see the same kind of distribution for Queens, Staten Island, and Brooklyn. However, we see a much flatter distribution for the Bronx and Manhattan. So this is something that we're going to keep in mind, and it will inform our decisions when it comes time to actually build the model. So after we visualized response time, we now want to formally test the relationship between response time and some of our predictor variables, specifically borough and complaint type. So from those graphs we just went over, we can come up with some questions. In my opinion, these three kind of pop out the most. Does response time for street floods differ from clogged basins? Does response time depend on the borough the incident occurs in? And does the relationship between complaint type and response time depend on the borough? Also, in that third question, implicitly, there is a fourth question. Does the relationship between borough and response time depend on complaint type? Basically, we're asking, is there any sort of significant interaction that is affecting the relationship? So the appropriate test here is a two-way ANOVA. ANOVA is short for analysis of variance. Just in simple terms, a two-way ANOVA is a statistical test that examines how two predictor variables impact a result. So it will first take the predictors separately and see if they have a significant impact on the dependent variable, which in our case is response time. But it also has another functionality in that it tests the interaction effect of the two variables. So in total, that our three questions from last slide are answered in one test. And for those of you not familiar with hypothesis testing, generally we derive conclusions from, this isn't the way, we derive our conclusions from p-values that come from the test, which are held in this last column here. A general rule of thumb is that if the p-value is less than 0.05, we conclude, we support our alternative hypothesis, which in this case will be that the variables are related. And we see that in all three cases, the p-value is very small. So our conclusion will be that these three terms here, descriptor, borough, and then the interaction between descriptor and borough, those are all going to be significant in predicting response time. And by the way, descriptor is just the binary variable for complaint type. So it's either street flood or clogged basin. And then a note, there are assumptions for the ANOVA. So this was using log transform data, which is important to make note of because results for log transform data are not necessarily going to hold for the original data. But this is an exploratory analysis, so we're just trying to get a sense of what's going on. Now we're going to build our actual target variable for the model that we'll see in the next section, which is this variable over 3 days. We're just taking all the incidents that have response time of over 3 days, and we're setting those to a value of 1, and otherwise this variable will be 0 for when it's less than 3 days. And again, we can ask similar types of questions. Does over 3 days depend on complaint type? Does it depend on location? Intuitively, we should suspect that the answer will be yes, since over 3 days was built off of the response time variable, and we already tested that. But we can do it again. This time, since over 3 days is a categorical variable, meaning it only takes a finite number of values, we will use a chi-square test for independence. It's essentially, though, doing something similar to what the two-way ANOVA was doing. It's determining if there is a dependency between the predictors and the response. And since it's categorical, it's generally used with contingency tables, which is what this code is doing here. It's generating contingency tables for over 3 days and descriptor, and then over 3 days and borough, and then it's running the tests for each. In both cases, the p-value is very small. It's less than 0.001, which again would be less than the 0.05, which is the general rule of thumb. So we would conclude that over 3 days depends on complaint type and borough. And so this kind of result, along with the previous results and the visualizations, are all going to give us a better understanding of the data and will inform our model that we're going to be building. It will help us select variables that we think will have a significant impact. And that's kind of the goal of exploratory analysis. And I will leave it there. Thank you all. I hope you found it informative. There's a link to the full project and the sources for the slides there.
So now we are going to model the occurrence of overly long response time. My name is Alyssa Horn. I'm a junior applied data analysis major with a domain in public policy. In this presentation, we'll build a logistic model to predict which flooding complaints are likely to take more than 3 days to resolve. By analyzing factors like location, time, and weather, we try to identify patterns that can explain why some complaints take longer than others. So first we have to import our relevant data sets. So we start with the sewer complaint data that we've been working with this far. And we're also going to add in rainfall data. This data shows daily rainfall measurements, including the date, time, and amount of rainfall recorded. And we're also going to add in ACS 2023 data. This data shows demographic and income information for each zip code in New York City, like ethnic populations, household income, and total populations. And we're also going to add in ZipLands data. This data shows the land square miles for each zip code in New York City. So we're going to start with some simple cleaning on these imported data sets. First, we have to standardize the column names of the newly imported data sets to match the rest. So, like John was saying earlier, we make the column names lowercase and add an underscore instead of a space. And we're going to rename the zip code columns to match for merging purposes. And then we create our modeling data set. So we need to choose predictors that we think may have an influence in determining if a complaint takes over 3 days. We can use a range of predictors, including things like neighborhood features, time, weather, and demographics. And we also made a rush hour variable, which includes times from 7 to 9 a.m. and 4 to 7 p.m. to see if that influences if a complaint takes longer. And we're also going to fill missing values. So to create the logistic model, the data can't contain missing values because it needs a complete set of information to learn patterns and make predictions. So to resolve this, we fill the missing information with 0 for amount of rainfall, because if it's missing, we just assume it didn't rain. Unknown for categorical variables. And we're going to use a KNN inputter tool to fill missing numeric values. This tool looks at other similar values and makes a guess based on those values. And lastly, we're going to get dummy variables for categorical columns like borough or city. The model can only understand numbers, so we turn those words into columns of 0 and 1s, and this allows us to include these categorical variables as predictors. So to model this, we're going to use a linear regression model. A linear regression model looks at the relationship between 2 or more things to see how they're connected. It finds the best straight line that shows how changes in one factor can help predict changes in another. And lasso regression is a type of linear regression that helps make better predictions by selecting the most important variables and shrinking the less useful ones to 0 and removing them from the model. Some benefits of lasso is it prevents overfitting, which happens when a model is too complex and performs well on training data but poorly on new data. So to make sure that doesn't happen, we split the data into training and testing data, training being 80% and testing being 20%, to verify the model's not overfitting and remains consistent across both those data sets. And Lasso also uses L1 regularization, which adds a penalty for using too many variables, which forces the model to say simple. And it's useful in dealing with many variables, creating a more efficient and accurate model by keeping only the most relevant information. So when we run the lasso model on our training and testing data, we get back 2 confusion matrices and also the accuracy, precision, recall, and F1 score of both the training and testing. So the confusion matrix is a table that shows how well a model's predictions match the actual results. So here we can see that the model correctly predicted 887 complaints as not late, and it correctly predicted 304 complaints as late. And now to move on to the accuracy, precision, recall, and F1 score. The accuracy, we get about 64%. So the model correctly estimates the wait time about 6 out of 10 times, while the other 4 out of 10 times it predicts longer or shorter times. And for precision, we get 35%. So the model correctly identifies late complaints about 3.5 out of 10 times, while other 6.5 out of 10 times it thinks a complaint is late when it actually is not. And for recall, the model catches about 3 out of 4 late complaints, while the other 1 out of 4 times it misses a complaint that actually took over 3 days. And lastly, the F1 score is the balance between precision and recall. So this is the balance between calling things late and things actually being late, and we get about 48%. So our model can also generate an ROC curve, which stands for Receiver Operating Characteristic Curve. And this is showing the training and testing AUC, as you can see in the bottom right. The AUC is a score between 0 and 1 that shows how well the model can separate late complaints from on-time complaints. 1.0 would be a perfect model, meaning the model would always correctly identify late complaints, while a 0.5 would be random guessing, where the model is no better than flipping a coin. Therefore, our model is about 73.7% effective at telling the difference between complaints that are late and those that are not. We can also find the most important predictors of over 3 days. Our model can show us how much each predictor influences whether a complaint takes more than 3 days to complete. The coefficient shows how much the feature increases or decreases the likelihood of a delay. And the odds ratio, if it's greater than 1, means it increases delays, and if it's less than 1, it means it decreases delays. So here are the top 10 predictors. So the first 5 are some of those categorical variables that we split up with the dummy variables. But in here, there are things like community board, city, zip code, and weekday. So the results we can get from that are weekday complaints take longer. So if you report an issue Monday through Friday, it's more likely to be delayed than if you report it on a weekend. If you live in Queens, Brooklyn, or the Bronx, your complaint is more likely to take over 3 days. And with that being said, some zip codes and community boards have slower response times. And if you're in Queens, you should expect a much longer wait compared to other areas. Additionally, larger areas experience longer wait times. So if you live in a big neighborhood with lots of land, response times tend to be slower. And surprisingly, complaints during rush hour don't seem to get delayed more than those at other times. And your neighborhood's income or racial makeup doesn't affect response times. And lastly, whether your area is wealthy or has a high population of a certain group, it doesn't seem to change how long it takes for a complaint to be resolved. So the main takeaways are, if you want a faster response, report your flooding complaint on a weekend or holiday. If you live in Queens, Brooklyn, or the Bronx, expect a longer wait. And some community boards get worse service than others, particularly in Queens. Thank you.
Good afternoon, everyone. Before getting started, I wanted to introduce myself. So my name is Amar, and I'm a senior studying actuarial science and statistics, double majoring. And I'm very excited about this project because it's the first time I built a model. So what am I going to explain in this part? So we cleaned the data, we visualized the data, we looked at the over 3D complaints, we did some hypothesis testing. So now what? In this presentation, we're going to analyze the complaints and examine different variables such as rainfall, geography, and socioeconomic factors to see if those variables can help us predict the complaints. And for this part, we're going to compare two regression models, Poisson and negative binomial, for predictions. Before getting started, let's look at our data sources. The data used for this is 4 data. 1, the complaint data we use for complaints. 2, the rainfall data, which has the precipitation levels for rainfall. And then 3, the New York zip code landscape, which has elevation, slope, etc. And then lastly, ACS 2023 census data, which has demographic data such as population, unemployment rates, and education, and socioeconomic factors, which can help us predict. So before we start, we have to first data process. So the first thing that I did was aggregate the complaints by zip code. This can help us identify specific zip codes to help identify high-risk areas. And this can help us use to predict and mitigate future flood complaints. The next step is merging all the data sets that I just talked about. First, the rainfall data. It can be a key factor in influencing flooding complaint, which is predictable. And by merging this data, we can assess the relationship between rainfall and complaint volume. And that's we can see if there is a relationship, and if so, is it a good predictor? So what we did here is just fix some date formatting issues and then merge it with the original data that we have that was clean. And next data that we added was its zip code level features, which has unique characteristics such as I mentioned, elevation, and in previous services that can help us also get new insights if these predictors are helpful in predicting complaints. Next, we did some feature engineering. We created some lag variables. Introducing these variables help us understand how past conditions might influence future or current patterns. And this approach can help us capture trends in complaint frequency and enables predictive modeling. So the 2 lag variables that we created is the precipitation. So it looked like a previous days of precipitation. And then the next one is the complaint type. So it looks at the catch basins complaints for the previous day. And the next feature engineering that we did is filtering the data from March to November, which eliminates month that has minimal flood impact, which can disrupt our data. So this improves the accuracy. So it makes clear the seasonal trends. So now to the important part, statistical model. So as I mentioned in the beginning, we're going to use 2 models to model the prediction of the variables. And we're not using linear models here because this is a count. These are for count models, and a linear regression is not very ideal for such modeling. So as I said, we're going to do a Poisson versus a negative binomial. And the main difference is the Poisson assumes a complaint occurs at a steady rate, and it is very simple and works well if the complaints do not vary that much. The next model that we're going to compare is the negative binomial model. And it's more fit or better if there is unpredictability or variance between the data sets. Like, for example, in this example is heavy rainstorms, infrastructure failures. So this can handle spikes in data sets better. So what I did was I used all the variables that from the data sets we uploaded, such as elevation, demographic data, precipitation data, and groups used all of those variables to figure out if they are good predictors, and if they are, which are the best predictors for this. So now let's go to the results. So when I ran both models and did a model comparison, this is the results I got. And we can see that for the log likelihood, the negative binomial is higher. And basically the log likelihood measure how well the model fits the data. So now we can see that here, the negative binomial is better than Poisson if we look at just the log likelihood. If you look at the IAC, which a lower number is a better model, and AIC basically balances the fit of the data and the complexity. And as we see, negative binomial again is lower here. So what are the key insights? Since Poisson assumes that the complaints are in a steady rate, it is less effective here because we know that complaints do not happen at steady rates. So the negative binomial is a better fit here because it accounts for variability for flood complaints, especially for areas with unpredictable surges or for scenarios where there's an unpredictable event. And we learned that zip code features matter. They help us predict, or they have some significance in helping us predict the complaint pattern. So what are the best and strongest predictors? From the results, I realized that the prior day complaint was the most powerful signal. So so we can say that the complaints from the past tend to persist. The second one was elevation. So higher elevation in zip code predicted more catch basin issues, possibly to do a concentrated runoff. The third one was impervious surface and areas with more of that, so a higher complaint prediction. And lastly, which also makes sense, precipitation. The lagged and also the same data, it showed us that these effects have a slightly more predictive nature than the other variables, with the lag complaint being a higher predictor. And also the other variables were also a good predictor, such as high density areas, the socioeconomic factors, but these were the strongest and top 4 predictors from the model that we got. So conclusion, the key takeaways from this analysis is the negative binomial is a better model for predicting complaint volumes. The second one is that data sets or variables such as rainfall, geography, and past complaints can impact future complaints or can help predict future complaints. So all in, this model or other models like this can help plan or predict flood response strategies. And thank you very much. And these are the sources where I got the code. Thank you.
Oh, okay, great. I just had a question about cleaning the data to try and figure out when you're looking at some of those open and close times for the 311 complaints. Was there any type of follow-up to make sure that that complaint was actually addressed rather than just closed? Is there any quality control in terms of seeing if the 311 complaint was closed because the problem was fixed, or if it was closed because someone looked at it and said, we can't do anything about it right now? Like, is there any way to tell that within the data?
Oh, in the data, there is a field called updated date, but we don't know. We have no idea whether the problem is just solved because it's solved, or for what other reasons. That's something we don't know.
I do see a question in the chat from David, and David has asked, would the result possibly vary with multiple years included, such as wet years and dry years, etc.?
I think I would expect that. This data set, just to reduce the data set for the students to work on, we only used the 2024 data. So I expect the severity will be different across years. On the other hand, I think we would expect the important factors, like the important factors Amar presented in last part of the presentation, the important factors such as elevation, and the lag count. Those variables, I would expect they will stay important even for a dry year. We didn't do that. We can check that out.
And it looks like we have a question from Priscilla, who's a former DEP sewer analyst. By regulation, clogged catch basins are required to be inspected within some period of the complaint. If they are found to be clogged with debris, there's another regulated period as to when that needs to be cleaned. Very interesting, Priscilla. Thanks for that inside knowledge.
Yeah, one of the reasons we wanted to use the number of catch basin complaints is that we expect when there are more clogs in catch basins, then we might expect more flood street. We cited that we have 2 papers worked by a professor from CUNY University. Actually, I recently started working with him, and he suggested this kind of causal framework for us to investigate. And that's why I put this as a midterm project.
Hi. I guess I just have a question for the students. What policy prescription do you think is like your main takeaway from what you've seen, either cleaning the data like at a basic level or maybe with your final analysis? I'm just kind of curious about what you think the real world takeaways would be. So if you're talking to someone from DEP or someone else in New York City government, what would you say as a result of your analysis? What points do you think are important as takeaways? Just kind of more holistic takeaway from your project.
I would first say, like, as we first explained the part A, is the data collection process. We saw that a lot of the data points were either redundant or empty. I think that's like in the basic kind of recommendations. But from my part, I would say a recommendation would be is looking at data that we've discussed in both models, in the negative binomial and the Poisson model, such as the previous day complaints, the precipitation and elevation, and using those kind of data to either predict or forecast possible complaints and prepare based on that. And also we can look at the visualizations. We saw that there were areas where it was concentrated and densely has a dense amount of complaints. We can prepare to have a more kind of infrastructure there, or prepare to have a lot of complaints there. So we have the people who are responding to these ready for those kind of complaints.
That's great. Thank you.
One thing I would say is that I get the impression that this 311 data set, there are multiple different agencies that are inputting data into it. And you can kind of see the effects of that in the terminology that's used between variables, or the fact that some columns are almost entirely empty. One general recommendation would be to try to standardize the way that all these different agencies are inputting their data, because I think they all have their own systems that all work independently, but sometimes they seem like they don't necessarily line up with one another.
Thank you.